Okay, hey guys. Sorry these are being posted a little late. We are going to be going over the notes from lesson 4. We started it a little bit last class. It's this lesson here. So I'll just do a quick review of what our bases are and stuff. You can skip through that if you want. I'll put a mark in the notes where you would skip forward to for that. Basically, quick reminder, we're doing volumes based off of our bases on our x and y plane. So if you think about it, remember we talked about if we have our xy planes, we have something graphed, it could be a circle. What we're doing is we're saying, okay, I'm rotating this now. So our xy plane is now an xyz plane. This is our x, our y, and now we call this our z-plane. We didn't really talk too much about that. Don't worry about it. It's just saying we're in 3 dimensions now. So now we have our circle here. What we're doing is just saying, what happens if I say, okay, there's a chunk here, and I'm saying, oh, well, there's an equilateral triangle, or there's a semicircle, or isosceles triangle, whatever you want drawn on this. So we also talked about semicircles. So we would have a circle base, and then if we cut that chunk out, we'd have something here that looked something like so. Okay. Not the best drawings, but it helps you get the idea of what we did on class last time. So go ahead and open your notes. We're going to be going through that first model problem. So if you look, it should be page 17. We're going to be doing model problem number 1. So what we're doing with this is we're going to be doing these 3 steps. We're going to determine our true volume of each cross-section, and then use our limits and integrals in order to find that volume of our solid. So don't panic. It's not that bad, I promise. All right. For this one, we're on page 17. This is model problem 1. Okay. For this first model problem, it says, okay, you're going to have a base. So I'm going to draw this on our xy plane for us. It's the graph x plus y is equal to 1. So it looks a little different than the way we're used to seeing it. All we're going to say is, okay, well, what happens if, my x is 0? Well, my y would be up here at 1. So that's this point. And if my y is 0, well then x equals 1. So it's down here. Connect those 2 dots, we make our line. It also tells us it's bound by the x and y axis. So this is my x and y axis here. This is my line. It's going to be all the area in between here. Next, remember, we always want to draw that box in, so we remember, okay, I'm taking a slice out of this, and that's going to have a cross-section of some shape. So for these ones, our slices, they say they're isosceles triangles, but they're a particular type. They're a right triangle. So I'm actually going to draw them kind of on their side, because one of those legs is actually our L. So here it's saying, okay, if I took this part would be our L, which is here on our graph, this height. So the length of our leg, remember, is on our graph, so it's going to be this side of our triangle. Since it's a right triangle, this is here. These are the same length. So if we think about the area of that triangle, it would be 1/2 base times height. Well, our base and height are the same thing. But we're not worried about area, we're worried about volumes. So remember, the reason we draw that chunk is because we're actually taking part of a volume out. So this part here, this distance, that's our dx here that was determined by how much of that slice we took out. So this is dx. So to the right here, I'm going to say, okay, my volume, in that case, well, it would be a 1/2 length squared, but times that dx, because our area of the triangle and the width. Now, if we want the area of this whole shape, if this is our base, we need to do an integral. So our v of the solid is going to be the integral. Well, my bounds are determined by x because we're using dx in this one. So if it starts from here and goes to here, it's going from 0 up until 1. So 0 to 1. Now my function, I need to know what my L is. Well, if I look at my graph, that's going to help me. That's why we draw these visuals. My L in this case is just the height of that function here. If I want it in terms of x, I'm just going to subtract my x over. So what that means is L is just equal to a negative x plus 1. So here, integral 0 to 1. This is now a 1/2 negative x plus 1 squared dx. Okay, from here we just need to solve our integral. First step is going to be to FOIL this out though. So this is going to be equal to the integral from 0 to 1 of a 1/2. And now we're going to have an x squared minus 2x plus 1 dx. Last thing we're going to do here, take our integral. So 1/2, we now have a 1/3 x cubed. We have a minus x squared plus x. And we're evaluating from 0 to 1. When I plug 1 in here, we'll end up with a 1/3 minus 1 plus 1 minus 1/2. Well, when I plug 0 in, these all end up being 0. So 0 minus 0 plus 0. All those cancel out still. So last thing, our 1's cancel, leaving us behind with a 1/2 times 1/3, which is a 1/6. That is the area of that volume created by something with this shape of a base and triangles coming out from it. So for model problem number 2 here, we look at our problem. It shows, okay, we are going to be doing a calculator active problem. So if you don't have your calculator with you right now, go ahead and pause the video and grab it. We are going to be going through how to find these on our calculators a little bit. We're still going to draw a visual so we have something we can work with on our papers though. So what we're going to do first is we're going to say, okay, I have that function they give me. I'm going to graph that in my calculator, and then I'm going to draw a visual of it on my paper. So if you take out your calculators, what you're going to do is you're just going to turn them on first. Step number 1, always. Okay, so I already have this graph, so I'm just going to go there. So if you look here, all I did, sorry, it's a little gross on the recorder. If you click tab, you'll see, okay, in F1, I just typed in my equation they gave me, the 2 times e to the x plus 1. Click enter, it will graph it for you. The other graphs we don't really need to type in, so go ahead and pause this and type in that function now. Okay, so what I'm going to do is on my paper, I'm going to draw this visual for myself. Okay, I have a function, it looks something like this. Here we go. But it also goes ahead and says, well, we're also not going past -1, or x. So we have this line here as well, x equals a -1. And it's bound by our y-axis, which is here. So if we think about this, the area we care about is just right here. Once again, I'm going to draw that box in just so I get an idea of where my slices are coming from. Okay, they're there. These have a width of some x that we call dx. Now, our slices for this one is another special type of triangle they gave us. Instead of an isosceles right triangle, they told us we have equilateral ones. So on your paper, draw an approximate equilateral triangle. I'm a little sideways. Don't mind that. What we're saying is with our equilateral triangles, these still have some width here. That's this side here, that chunk, our dx. These are laying on our base, and they have this length here. And if I look over here, it's just going from my x-axis up to my line. So that means this L here is going to be equal to my function, 2e to the x plus 1. What we need to be careful with, though, is saying, okay, if it's 1/2 base times height, our height, though, is no longer just L. We are now looking at what's called a 30, 60, 90 triangle. So if you remember 30, 60, 90, our rule says, well, if this is x, this height here is a root 3 of x, and our hypotenuse is 2x. That's because this is coming from a split in half equilateral triangle. So we have 60, 60, and 60. Well, if I split that 60 in half up here, well, now it's 30. So this is x. Well, this would be 2x. That means for my height in this case, my h here, it's going to be 1/2 my length, because x, I have to break that in half from my hypotenuse. So it's going to be 1/2 the length times, well, that root 3 here. So we can simplify that into a root 3 over 2 times L. That means the volume that represents that slice, that's going to go ahead and be a length times a root 3 over 2 times their length. But this is all times another 1/2 because of that area formula for a triangle. 1/2 base times height. Altogether will look like this. So that means our volume of our actual solid that we're finding, we're going to do an integral. If I look over at my visual, I give myself, okay, it starts at -1, it's going all the way up to 0. -1 to 0. Now my function, I'm going to combine my constants. I have a root 3 over 4 times an L squared. So what you're going to do on your calculators, go ahead and grab those, is you are going to create a new page. So you can either do that by clicking Document or Control Add Page. We need a calculator. Okay, so what you're going to do on your calculator is you're going to go, and we're going to make our integral here. We're going from -1, we're going all the way up to 0. Our function now is root 3, so it's going to be over 4, times our variable f1 of x, because our L in this case is just our function. So f1 of x, the sun is killing me. Okay, f1 of x, this is in terms of x, end parentheses, it's a squared, end parentheses, dx. Click enter, it tells us what our integral is here. So what we're going to write on our papers is just our v of our solid is equal to 2.2767. Box your answer. Okay, so sorry about the light stuff there. If you couldn't see it, this is the work we did, and on the calculator we had ended up with that 2.2767, which is why we were using that. So for this video, I'm just going to do those first 2 model problems. I'll do model 3 in a second video for you guys to watch. If you feel comfortable, go ahead and start trying some of that practice or working through your problem sets.